I am Rogue. Welcome back. So last time you saw that subgroups are subsets of an even larger group that form groups under the same sort of group operation. What we basically said was a subgroup is a subset of a larger group G that has a group structure of itself with respect to the same group operation as the larger group G. A relevant sort of operational question would be that, okay, given a subset of some group G, how do I know that that subset is a subgroup? Well, the most straightforward sort of like way to do this is to actually go through each and every axiom of a group and verify that it holds for that subgroup with respect to the group operation. That is, first of all, check that it's closed under multiplication. That is, like, given two elements of the subset, when you multiply them with the group operation, you ought to obtain a third element that is in the subset itself. The second one is check that it contains an identity element, and it turns out that the identity element for any subgroup in G is actually the same as the identity element for the group G itself. The third one is check that every element in the subset contains an inverse under the given operation. That is, like, if A is an element in the given subset, then it must be the case that there's just A inverse in the same subset, such that A times A inverse under the group operation gives the identity element of the group. So that's kind of tedious, right? And you might ask, is there like an easier way of checking if a given sort of like subset is a subgroup? In fact, there are many sort of like ways to do this, but some of them are like very specific, right? So we might, as we'll see in the future, like you might choose to demonstrate that a given subset is like the center of a group and immediately conclude that that's a subgroup because centers of a group are always subgroups. So there are these type of like sort of very highly specialized ways to check if a given subset is a subgroup. But is there a sort of like an easier but very general way? Well, there actually is. It's called the subgroup criterion. And in this video, we will state and prove the subgroup criterion. Before jumping to the proof and statement of the subgroup criterion, let us actually first discuss four terms in mathematics that are often confused. These four terms are proposition, theorem, corollary, and lemma. To begin with, all four are statements of mathematical truths, or they are mathematical statements about mathematical objects and the relations thereof. So let us actually start with theorems. Theorems are often very fundamental, very overreaching mathematical statements with oftentimes lengthy, multi-staged, and complicated proofs. So the fundamental theorem of calculus, the fundamental theorem of arithmetic, Fermat's last theorem, and the Pythagorean theorem should ring a bell. Oftentimes, as you can see in the examples that I've just mentioned, theorems could even extend as far as being the sort of bedrock of entire subfields of mathematics. And as readily demonstrated, especially in the case of Fermat's last theorem, their proofs are oftentimes very complicated, lengthy, and multi-staged. When it comes to propositions, one can think of propositions as sort of like scaled back, not as much influential sort of theorems. They're not as fundamental, and their proofs are not very lengthy, multi-staged, or complicated. So one can think of propositions as sort of like tiny theorems. On to corollaries. Corollaries are oftentimes propositions, in fact, that immediately follow from a given theorem or a proposition, right? So corollaries oftentimes do not require proofs. They're oftentimes statements of a theorem, an already verified theorem, or an already verified proposition holding in a specific context. So they're sort of like gifts of a given theorem and a proposition. Just like Herodotus said, Egypt is the gift of denial. I like to say that corollaries are gifts of theorems and propositions that immediately follow. But don't be fooled in sort of considering that corollaries never require proofs. In fact, as we will see, some corollaries actually require like some type of proof. But the proof, like 90% of the content of that proof has already been done. It's sort of like referring back to like a huge theorem or a proposition. And you might have to prove like some things that sort of like lay out the groundwork in that specific context. The fourth one is lemma. The nomenclature for lemma is actually very distinct from the previous three because it's not of scale or of triviality. The distinction is actually of utility, and that lemmas are theorems, propositions, or corollaries that are used as intermediate steps in the proof of an even larger theorem, right? So it's sort of like their use that sort of gives them this name. So any of the previous three could be lemmas for the proof of a given theorem. The statement of the subgroup criterion is as follows. Given a subset H of G, to verify that H is a subgroup of G, it only suffices to show that, first, H is non-empty, and second, given two elements of that subset H, it's enough that we show X times Y inverse is also in H. So let's move on to the proof. Since the statement itself is a by implication, we would have to prove the left and right implication separately. So let us now start with the rightwards implication, which is actually like the easier implication to prove. So given that H is a subgroup of G, it's true that H is non-empty, right? So since it's a subgroup and it must contain the identity element. So condition 1 holds. And for condition 2, it's actually wise to see that condition 2 sort of like sandwiches the closure under multiplication and the closure under inverse conditions onto 1. So given that H is a subgroup of G, is it true that condition 2 holds? Well, let's see. So given elements X and Y, it's true that elements X inverse and Y inverse are also in H, since H is a subgroup, which is closed under inverses. So given that X, Y, X and Y inverse are all in H, it's also true that X times Y inverse is in H, because H is a subgroup closed under multiplication. So the rightward implication holds. Let us now move to the leftward implication where, given the two conditions here, H is a subgroup of G follows from these two. Well, given that H is non-empty, there must be some element H, small h, and H, right? And by the second condition there, H times H inverse is also in H, but H times H inverse is the identity element. So it must be the case that the identity element is also in H. So let us now move on to closure under multiplication and closure under inverses. Well, in the second condition, let us take X to be the identity element and Y to be some random element, say X in H. So the identity element times X inverse must also be in H. Therefore, H is closed under inverses. Is H closed under multiplication? So this is sort of like a cheeky proof, which is quite straightforward actually. So note that given X and Y, we wonder if X times Y is in H. Well, the way to proceed is as follows. Since H is shown to be closed under inverses, right? X, Y, X inverse, Y inverse are also in H, right? So when you consider X times Y, we note that x times y inverse must be in H as per the second condition. But x times y inverse is x times y, as desired. Let's now move to the demonstration of the subgroup criterion is at work. So I was actually just reading this week that even though the immediate cause of the First World War was the assassination of Archduke Franz Ferdinand, it was noted that one of the sort of like major long-term causes of the war was the sort of lobbying from big military sort of like contractors, or like the military industrial complex that was pushing, that has sort of like built up novel weapons, very powerful weapons that have never been tested. So like they were actually like pushing for war. Like, and no matter how vile humans are to sort of like try out something that we've just invented, right? And luckily for us, it's a very good weapon, a weapon for good as well. So let us try out the subgroup criterion here. This subset is a line in the complex plane. Is it a subgroup of the group of complex numbers under addition? Well, let us go through each condition. First of all, it's not empty and it contains the identity element 0, since 0 plus 0i is 0. It's found in C, in the subset C. Second, it's closed under addition, since given a plus ai and b plus bi, their sum equals a plus b plus a plus bi, which is in C, since a plus b equals a plus b. Also, there's closure under inverses, where for any real number a that forms a plus ai, it turns out that there's sort of like, there's an element minus ai, such that their sum is always the identity element, right? So that's its inverse. Let us now move to example 3, where the power of our weapon for good, or good weapon, they don't commute, I guess, are sort of like put on display. Let us consider the complex plane once again as a group of the complex numbers under addition, but a different subset. That is a subset of complex numbers with norm 1. And this forms a circle of radius 1 in the complex plane. Is this a subgroup? Well, let's see. By the subgroup criterion, first of all, it's not empty, right? Since it contains the number 1, which has norm 1. And it turns out this is like the identity element as well. And for the second condition, first of all, we should note that all elements on the complex, this circle, complex elements on this circle could actually be expressed as e to the some real number a times I. All sort of like complex numbers with norm 1 can be expressed as such. So given two such elements, e to the ai and e to the bi, is it true that e to the ai times e to the minus bi is in sort of like this subspace, this subgroup? Let us see. Well, that product gives us e to the a minus b times I, and a minus b is a real number, and e to the any real number times I is a norm 1 vector. So this actually follows. So we're done. This demonstrates that this is in fact a subgroup of the complex numbers under addition. The last thing we need to sort of like look through is a corollary that actually follows from the subgroup criterion. As I've mentioned earlier, like this corollary is not the sort of like traditional corollary that is sort of like gifted trivially from a given proposition or theorem, such as the subgroup criterion. This is in fact one of those corollaries that requires some sort of like proof or like some sort of work. Well, so the corollary states that given H, which is a finite subset of G, then for H to be a subgroup group of G, it only suffices. It suffices to only check that, first of all, H is not empty, and second, H is closed under multiplication. Note that the first condition is the same as the subgroup criterion, but the second sort of criterion is much simpler than the second criterion for the subgroup criterion, since it avoids implicitly sort of like jumbling up the multiplication, the closure under multiplication and closure under inverses conditions, and only requires closure under multiplication is verified. Let us see why. I apologize for sort of like the back stripe. I was too lazy to go retype the LaTeX file and import it into this presentation, so I just put on a black rectangle over to cover the fact that I just said if H is a non-finite, a non-empty finite subset, since non-emptiness is sort of like a checking condition and not a precondition. So, and the proof goes as follows, right? Consider like H a non-empty subset, right? It has to be non-empty. We'll check it's not empty. And once we sort of verify that it's not empty, we know that there's some element X in H, right? It's not empty. So consider like the sort of like sequence of powers of X as follows: X and then X squared, X cubed. And note that the powers of X are simply sort of like repeated multiplications of X by itself under the group operation, right? Note that since H is finite, these elements cannot all be distinct, that it has to repeat itself at some point. Like if X, all powers of X until like infinity are distinct, then H must be infinite, right? But H is finite. All these elements cannot be distinct. And you might say like, wait, like why cannot they be distinct? Why cannot they be outside of, like, why cannot we only consider like sort of like powers of X until like some power and then like sort of ignore the others? Well, mind you that we're trying to prove that H is a subgroup, right? So all powers of any given element has to reside within H, right? That's where we're trying to get to. And if H is to be a subgroup, then all powers of any sort of like element in H have to reside in H. So that's why. So note that like some powers like have to start repeating like at some point. So let's say like it's true that X to the A equals X to the B, where B is greater than A. That is like X to the A repeats itself at some point where X is raised to the power B. For some integers A and B, right? So by the left cancellation law in G, it turns out that this implies that X to the B minus A equals the identity element, X to the 0. And let's refer to B minus A as N, since like an integer minus integer is an integer, since integers under the operation addition are groups themselves closed under the group operation. So we're saying that there is some N in an integer N such that X to the N is sort of like the identity element. But this immediately implies that X to the N minus 1 is X inverse, since X to the N times X equals, X to the N minus 1 times X equals X to the N, which is the identity. And since the inverse element of a given element X is unique, X to the N minus 1 must be X inverse, right? So for a random element, where H is non-empty and it's closed under multiplication, right? We've demonstrated that the fact that it's finite forces H to be closed under inverses, right? So we only ought to check the two as long as H is finite. So this is a beautiful sort of like result that is sort of like, that is very interesting, and it follows from the subgroup criterion. Well, mostly so.